So, today we are talking about quantum numbers. Okay. Quantum numbers are arbitrary numbers that explain the location and angular energy of electrons. Is it not covering?
It just says that.
That didn't work. Whoever's listening to this recording right now is going to be thoroughly confused.
Why would someone do this?
There's a number of people that aren't going to be here today and tomorrow, so I'm recording the lecture. All right. Number of arbitrary numbers that define or map out where an electron is in an atom, or where the probability it would be in an atom. As we figured out yesterday, due to the uncertainty law, is it uncertainty principle? Why can't I think of it right now? Heisenberg's uncertainty principle. The uncertainty principle. There we go. This created or came up with the idea of the electron cloud model of the atom, correct? What does the uncertainty principles tell us?
Are those the three you wrote down?
Three I wrote down of what? About the Bohr atom? No.
It is impossible for us to know that. Whatever that says, position and energy.
Yeah. It is impossible to know the energy and position of an electron. Okay. If we know where it is, we don't know how much energy it has. If we know how much energy it has, we don't know where it is. Okay? Which is why we have that electron cloud model of the atom, which is that little nucleus and the dots. This is why it's also called, oh my goodness. Whatever. It is the nucleus with a bunch of dots around it. It is the probability of where electrons can be around the nucleus. Okay. This forms itself. I guess I could have just done that, couldn't I? We'll do there. Okay. We know electrons have to be in certain orbitals because they have specific energies, but we don't know, don't know that the electrons are in rings. Okay, the rings would tell us exactly where that electron is. Okay, so now our orbitals have different shapes. I want you guys to pull out your periodic tables if you don't have them, or if you do have them.
Can I share a lesson?
Mm-hmm. I'm going to do a crude drawing of a periodic table here. Lanthanides and actinides. All right. So, the orbitals that we have inside of an atom, where these electrons can be, are labeled as S, P, D, and F. I'm actually going to, nope, eraser. Put them in different colors. S, P, come on. B, D, and finally F. So those are our 4 different orbitals. Each of these orbitals have different sizes, orientations, so on and so forth. Okay? But the average shape of each of these orbitals looks like so. An s orbital looks like a sphere. Okay. It is a general just sphere of probability of where that electron could be. P orbital looks like a dumbbell. Okay. The p orbitals can go, we have to start thinking in terms of 3D, so x, y, and z axis. X, y, and z. P orbital can go on the z axis, the x axis, and the y axis. If you try and change the orientation of the s orbital, it's just a sphere, so it looks the same whichever way you turn it. Does that make sense? The d orbitals look a little bit different. I'm not going to draw all of them. We'll get to that later. But the d orbitals just look like 2 dumbbells. Those are situated in different orientations around the 3D plane. And then there's one extra that looks even more different, where it's 1 dumbbell and then a donut around the center. If you're wondering how we got these orbitals and how they look like this, it's all math. Just intricate math that gives us these shapes. Okay. And then finally, F is just 3 sets of dumbbells. And then you have one that's coming out towards you and one that's going back into the plane. And then the weird one for F is a dumbbell with 2 rings. Okay. Now, how we can tell where an electron falls, whether it's going to be in an s, p, d, or f orbital, is based on the periodic table. The periodic table itself is kind of crazy. The s orbitals, if you're looking for an electron that is in an s orbital, it is in this section of the periodic table. That is groups 1 and 2. So hydrogen's electron is in an s orbital. Helium also is shifted into this column. So helium, which is normally over here, gets shifted over to right next to hydrogen. Okay, so those first 2 electrons are in an s orbital. Then the p orbitals are over here. Those are all the p orbitals. Okay, that is groups 13 to 18. The d orbitals are the transition metals, which I now realize are very small compared to everything else. But the d orbitals are in the transition metals. And the f orbitals are in the lanthanides and actinides down here. This is very abstract stuff, I know. Okay, but it'll make more sense here in a second. You guys with me so far, though? Each of these shapes are possible areas where an electron can be based off of its energy. Okay? Now, if you look at these orbitals, like the s, p, d, and f, each one has more curves than the one before it, right? This is how I remember the order of angular energy increasing. Okay? If you try to drive a car around the edge of the orbital there, for an s orbital, it would be pretty easy. You don't have to turn too much, but you have just a left or right turn the entire way. You can just hold your steering wheel there, and it'll take you around the sphere. For a p orbital, it's a figure 8. So you're going to have to crank on your wheel a little bit more, and it's going to have a little bit more angular force on you. You're going to have to lean into the turns more. Okay? And D, you're going to have to lean into the turns even more because there's even more turns. And then finally F, same thing. Okay? So the angular energy increases as you go from S to P to D to F. Does that make sense? And remember, these electrons are traveling around these orbitals. So if an electron is in the p orbital, it's like a car that is driving in that way. Okay, so that's angular energy. It's going to have a lot of turning energy. Does that make sense? Okay. So in generalized form, increasing energy goes this way. Questions so far? Okay. Can I move on or scroll down? Okay. Now, there are certain numbers that go along with these orbitals. We already know of one of the quantum numbers. Okay, it shows up in our Rydberg equation, and it's labeled as n. What is n? The principal quantum number. Okay. Principal quantum number. The principal quantum number tells us general energy, and is shown by the electrons period on the periodic table. Okay, so the rows on the periodic table, there's 7 of them. Okay, an n being 1 has a lower energy than an n being 2, and so on and so forth. Does that make sense? Do you guys remember my as electrons get farther away from the nucleus, they have more energy analogy with the meter sticks? Okay, this is the same idea. Okay, These electrons are getting farther away from the nucleus, and so they have more energy. That's what N means. Does that make sense? Okay. The possible values for N are 1 to 7. Possible values for N are 1 to 7, and that's because there are 7 periods on the periodic table. Okay? Then, the next one is L, and it actually is a cursive L, so you have to write it like that. Okay? L is called the angular momentum quantum number. All this means is what shape is the orbital. Is it an S, P, D, or F? Okay. The possible values for L are anywhere from 0 to N minus 1. Okay, so whatever N is, subtract 1 from that, and that's the maximum L that you can have. Okay, so if I have an N that is equal to 2, the possible L values I could have would be 0 or 1. Does that make sense? Yay, nay? Now these numbers, a 0 is an s orbital, a 1 is a p orbital, a 2 is a d orbital, and a 3 is an f orbital. All the sort of electrons that we will look at will be within these numbers. So even though n can go higher, which means your L can go higher, all of our L values will be between 0, 1, 2, and 3. Does that make sense? So the L number tells you what shape the orbital is, if it's an S, P, D, or F. Still with me? Okay. Can I scroll down? Yeah. There's 2 more. Third one is an M sub cursive L. So a little lowercase m with a subscript cursive L. This is called the magnetic quantum number. And it tells you what orientation the orbital is in. Okay, as we said before, the p orbital can be on the x, y, or z axis. The d orbitals have 5 different orientations. The f orbitals have 7 different orientations. Okay, so this one determines what orientation your orbital shape is in. Okay, possible values are anywhere from negative L to positive L. So if I had an L value of 1, which would be what orbital? P. Yep. It gets confusing because N can't equal 0, but L can. And so when L is 0, that's an s orbital. So that's the lowest. When L equals 1, that is a p orbital. And so m sub L could be -1, 0, or 1. And that tells you how many different orientations the p orbitals have. There are 3 different orientations. It can be on the x, y, or z axis. So it could be on the x, y, or z axis. -1, 0, or 1. Any questions so far? We've gone over a lot, and it's not necessarily stuff that's connected to the stuff we've talked about before. All right, finally, we have our last quantum number, and that is an m sub s. Okay, lowercase m with a subscript s. This is the electron spin quantum number. We'll learn about tomorrow some laws that go with these orbitals, one of which is called the, where is it? I believe it's Hund's rule. It's either Hund's rule or the Pauli exclusion principle. We'll get to it. Says that 2 electrons can be in any one orbital. Okay, so the p orbital, there's 3 of them. There's the px, the py, the pz, whichever one is on the x, y, or z axis. In each one of those, there can be 2 electrons. Okay, if you look at your periodic table, how many elements are inside the p orbital area in each row? P orbital. 6, right? We have 3 orbitals, the px, the py, the pz, and 2 electrons can fit in each orbital, correct? Which would tell you how many electrons would be in a single p orbital series. 2 times 3, 6. And there's 6 elements per row inside the p orbital area, right? Okay, that's how they match up. So the electrons are both what charge? They're all what charge? Negative. And so if you're having 2 of the same charge inside an area, they're going to want to do what? Repel each other. And they will. However, it's more bearable if one is spinning one direction and the other one is spinning, let's see if I can do it, one direction, and then, no, that's the same direction. There we go. One is spinning one direction and the other one is spinning the other direction. Okay, so ms is the electron spin number. It's arbitrary, but one of them would be a positive 1/2 and the other one would be a negative 1/2. A spin up or a spin down. Now, I know this doesn't seem like it matters, right? Like you just want to do chemistry, you just want to do the reaction. However, in order to understand how these electrons are participating in reactions, you have to understand where they are. And to understand where they are, we have to understand how to map them. And that mapping comes from the quantum numbers. So if you guys look at your periodic tables, kind of trippy. I'm going to scroll down so that's just white. There we go. All right. So if we look at our periodic table, let's say I want to map out all of the electrons in helium here. Helium has how many electrons? How many total electrons does helium have? 2. So helium has 2 electrons. It's in the first row, right? So what would its N number be? What would its principal quantum number be?
0.
It's in the first row. One. N would be 1. Okay, remember the N is based off of what period it's in. Okay, so both electrons that helium has would have a principal quantum number of 1. So we'll call this electron number 1, and this one electron number 2. Both of them have an N that is equal to 1. What are their possible L values? 0, and that's it. Okay, the L value is anywhere from 0 to n minus 1. Our n is 1, and so our range is 0 to 0. It can only be 0. Okay, so both of these have an L value of 0, which means they're in what shape orbital? S. They're in an S-shaped orbital, which is a sphere. Okay. What about m sub L, the magnetic quantum number? What are the possible values here? M sub L can be anywhere from, that's for an L that's 1.
0.
It's just 0. So M sub L can be numbers that are anywhere from negative L to positive L. In this case, our L is 0. And so the range can only be 0. Does that make sense? So our M sub L is 0, which means there's only one orientation that this s orbital can be in. Okay, it's a sphere. If you try and change its orientation, it's just going to look the exact same, right? And finally, we have our M sub s, our spin quantum number. There are only 2 values that these could be. And if one is positive, the other one has to be negative. It's arbitrary too. So we'll say this one is a positive 1/2, and this one is a negative 1/2. So this one would be spinning in one direction. And this one would be spinning in the other direction. questions, comments, concerns? Yeah.
So if you had more than 2 electrons, would it still not matter? And that's like the halves. Would you just split them up evenly?
It depends. So if they're in the same orbital, meaning they have the same numbers 1, 0, 0 in this case, if they have the same numbers up until ms, then you would just choose which ones get the positive and which one has the negative. Because there can only be 2 electrons per orbital. Now, if this was 2, 1, 0 over here. So if this was 2, 1, 0, and this one was 2, 1, negative 1, it wouldn't matter. They could both be positive because they're in 2 different orbitals. Does that make sense? Okay. Good question. Any other questions? We're going to do another example.
Today?
Yeah. Still got 5 minutes. Come on, Riley.
Okay.
All right. We're only mapping 1 electron this time. So there's going to be multiple different possibilities for the quantum numbers. Okay, so we're just going to label all the possible numbers for this electron. We're going to look at carbon. And its final valence electron. So imagine we are finding the number of valence electrons for carbon. We'd go to the period carbon is in, which is period number 2. And we start counting from left to right. 1, 2, 3, and 4. The last one lands on carbon itself. Does that make sense? Okay. So we're going to map out the possible quantum numbers for that 1 electron. Okay. That 1 electron is in what period? What row on the periodic table? First or second? Come on, Luke, speak up. It is in the 2nd row. So our n is going to be 2. Its principal quantum number is 2. Okay? Which means its L can be what, Riley? There's 2 different, it could be 1 or it could be one other number. Or 0. Okay, the possible quantum numbers for L is that it could be in 0 or 1. Meaning it could be in an s orbital or a p orbital, correct? Okay.
Circle 1.
In this case, we are looking at the electron that is right on carbon, which is in what area? The s or the p? It's in the p area, right? So this one would have an L value of 1. Does that make sense? Since its L is 1, its M sub L could be what possible numbers? Tegan.
-1, 0,
-1, 0, or 1. Okay, anywhere from negative L to positive L. Okay, this one we can't narrow down. We don't know what orbital it's actually in. Okay, we don't know if it's the px, py, or pz. Okay, so this one is going to have multiple different possibilities. And then the M sub S also has multiple possibilities.
Negative half or positive.
Yep, could be -1/2 or +1/2. And this would be the quantum numbers of, whoops, circle the wrong thing, carbon's final valence electron. Make sense? All right, we will continue this practice tomorrow.